Hello and welcome to part D of this homework number 3 for separation processes. Today is going to be a little bit of a longer video, just based off the criteria of this question. We're going to do some work on my iPad, we're going to do some work in Colab, we're going to do a little bit of everything. So I will read the problem statement to you guys so everyone's on the same page. For part T, we're going to first derive the material and energy balances around stripping and rectifying envelopes, which, as you can see, we have already done. Here's our stripping and here's our rectifying. We have already started on those in this homework. And then we're going to algebraically show how the graphical Ponchon-Savret method can be justified using similar triangles. And then for part 2, we're going to go into Colab and we're going to use a 45-65 mole percent methanol isopropanol or isoprenol, I hope I'm saying that right, feed with 96% distillate recovery of methanol and 98% mole purity. The reflux ratio 5, we're going to write the code to computationally generate a Ponchon-Savret diagram, and then we're going to demonstrate and explain the impact of varying reflux ratio. Again, this sounds terrifying. It's not going to be that bad. My camera is not focusing correctly. But yes, let's get into it. So, per usual, the first thing that I'm going to do here is draw a diagram. And first, I'm going to write part D so we know what we're doing. And the first thing that we're going to do here is draw, like I said, a diagram. So, per usual, at the top here, we're going to have a condenser. We're going to have an intermediate step here. And then we're going to have our larger distillate column here. And now, as you guys have seen multiple times, we have this vapor rising and we have this liquid dropping. Except here, this time, we are going to have a distillate value coming out here. And then we will also have this connecting with our condenser. I'm going to draw a C here. And then we're also going to have heat being added into that condenser. So the last couple things that we need to do for this is to draw the actual vapor going in that we're going to list as Vn+1, and then we also have the liquid that is dropping out that's going to be N, and then in here we'll have that distillation column labeled as N. And so from here we want to be able to draw a nice little box around this system, and to do that, we're going to take this and we are going to draw our box. It's going to start right here. It is going to go down. It's going to grab both of these arrows, so those are incorporated, and it is going to go right along this line right there. So now that we have completed this diagram portion, we are able to work into the, not working, energy balance portion. So first we're going to complete this energy balance section, and then we're going to actually move into the material balance. And so this energy balance equation is going to be listed as V to N+1 multiplied by the heat of vapor, H hat, heat of vaporization, Vn+1. And this is going to be set added to QC set equal to our liquid at N times H hat of ln plus our distillate. I'm going to move this over a little bit. Times our distillate times the heat there at the distillate. And then from here we are going to actually go straight to our material balance. And this is going to use that equation that we just got above. And so the first thing that we're going to do is obviously the vapor at N+1 is going to be equal to our liquid plus our distillate. And that is because whatever is leaving in this distillate is only composed of two things: our vapor. Oh my gosh, this won't work. Our vapor value here and our liquid value here. So now we are going to plug that into our next equation, which we will label as 1. And we are going to get y sub n+1 times v of n+1. We're going to set that completely equal to xn ln plus xd at the distillate. Now that we kind of going to be doing a like system of equations solve approach here. So we have now yn plus 1 times ln plus d. We're going to set that equal to xn ln plus xd times d, because we know that this is equal to this L plus D, so we just took that and plugged that in right there to get this equation. And now from here, we're going to divide all of these terms by D, and so you get not yet, I'm skipping a step. We're going to do ln, we're going to take this out. We're going to multiply this by yn plus 1 minus xn, and then we're going to say multiplied by D times xd minus yn plus 1. And now we're going to divide everything by d. And so you will get ln over d multiplied by yn plus 1 minus xn is going to be equal to our x at the distillate minus our y value at n plus 1. And this is actually the equation we've been looking for. This is the completed material balance for this problem. I actually apologize, I got a little bit ahead of myself. This is not yet the completed, this is not the final form yet. I got a little excited. So we're going to use that equation though, and we're going to rewrite that top section, and we are going to get L, it's right in green, ln plus D. We're going to take that and we're going to multiply it by our heat of vaporization at n plus 1. We're going to add that to our QC value, and we're going to set all that equal to our ln value at h bar ln, and we're going to add that to our distillate times h bar times d. And so now we want to get QC actually onto the other side, and then like we did in this one, we want to take out our ln and our d values. And so from there, again, I'm kind of skipping over some of the like in-depth algebra. No one, you guys, I'm sure, can do that on your own. So we're going to do ln times h bar v times n plus 1. And then we're going to subtract away our h bar of L at 1. And we're going to set all that equal to d times h bar at the distillate minus the heat of vaporization bar at n plus 1. And we're going to take all that and add QC over D. I'm sorry. Wait, I may have made a mistake here. No, I'm sorry. Yeah, wait, this is just QC. And now we're going to do the same thing as we did in the previous one, and we're going to do divide. I'm going to fix my camera actually. I need a little more room here. There we go. Okay, so now we're going to take this and we're going to divide everything by D like we did in the previous one, and that's going to get us at our final equation. So you're going to have ln over D multiplied all of this by h hat v n plus 1 minus h hat l n, and that's going to be equal to h hat at the distillate minus the heat of vaporization n plus 1 plus QC over D. Now this is our final answer, and then we're actually going to graphically prove why this works in 1 second. So I'll square that off, and that is the completed material balance for this system that we created. So as I said, we're going to now create a plot, and this plot is going to compare the vapor and the liquid composition at the same time. So we're going to draw a graph here. And this is going to be h bar, and this is going to be, as I said, the composition. And so we want two lines. We're going to do blue for our liquid, and we'll do red for our vapor. And then there's going to be a point up here that we're going to label delta D. And so now, before we start actually making these triangles, what you do is you draw a line straight down, and this is going to be equal to our xd value. And from here, you're going to go and make an equation labeled as delta D is going to be equal to h bar at D plus our QC value divided by D. So now the next part can be a little bit tricky, but so I want you to imagine that you can pick any point along this bottom line here, and let's say here, and what you do is you would create a straight line here, and then you'd also have a point that would connect them to this intersection line. And so we'll use gold here. Actually, let's just highlight it and let's use be really small. So you essentially have you would have three lines almost in a step function. I don't really like how that looks, so we're gonna do that again. You have three lines. You have one starting here going down, you have one going across, you have one going down, and then across. So you have four steps here that are equal to that triangle. And now what I want you to do is here, we are going to copy these, duplicate that, let's make it small. And then I want to go up here and grab this one. And so what we're going to say is now, I'm going to label these. This first portion over here, this is A. This portion here, we will say is B. The green here, this green one is going to be C. This purple one is going to be D. And then these have their own inherent value inside this. So actually, I'm going to zoom in here. A, B, C, D. Hope that makes sense. So this alone actually proves why this Ponchon-Savarith works, because it is taking this triangle and it breaks it down into separate equations that when we're able to say, like, it's almost like if you think about finding the slope, you know, like a squared plus b squared equals c squared. Instead of, you know, taking that linear path, you're able to use this equation that then creates step functions that gets you to arrive at the same place, just in a different way. And so we have proven that in our graph, and now we are able to, I'll add a new page. Oh my gosh, I don't understand why this doesn't work. Now we're going to do the stripping portion of this assignment. And so now doing this stripping section, we're actually going to take, imagine that we are going to be working like right down in here now in this section. So the bottom of this distillation column, which would be right here, and then all that stuff would be kind of up there above. So I'll draw a little bit of like this line so we know that there's stuff going on up there. And you still have your vapor going in, V, which we is n plus 1. You have your liquid leaving, and then, but now it's obviously going into that reboiler. So we will draw this little square here. As we mentioned, there is heat going in, which we will label as QB. And then we have our boilant leaving. And then again, we're going to draw that little envelope around it. So we have Q, B, and then our V and L values. And now we can actually go into our energy balance portion, just as we did up top. So the energy balance is actually just going to be one singular equation here. And to get it, we will just write this out. It is going to be V bar at n plus 1 plus H bar at V n plus 1 is going to be equal to our boilant times H bar at the boilant. And you know what? We're going to move this down. And that is going to be equal to our QB value, that is going the heat going in, plus our liquid value of N, and then our H bar at N. So that actually completes the energy balance. And now let's do our material balance, which is going to be a few more steps. So again, this is going to end up becoming a system of equations. So we're going to actually label this as 1, and then what we're about to get is going to be 2. And so this first equation is going to be, actually not 2 yet. We have to do a couple steps to get there. Sorry. So it's going to be L n bar equal to V bar n plus 1. And then that is actually going to, what else are we going to add? I think it's, oh, it's the boiling. Yeah. You can see the boiling right there. And so now actually we're going to get our second equation in the system. And that is going to be X L bar n equal to y n plus 1 v n plus 1, and then we're going to add that to our xb and our boilant. And so now kind of combining those equations, we are going to have x sub n multiplied by v bar n plus 1 plus b, and we're going to set that equal to our y n plus 1 times v bar n plus 1 plus xb and b. And now you can see we got that from this ln value being equal to that. So we just took that and brought it right down into there. And so now, next we can take that vn plus 1 out, and you get v bar n plus 1 times xn minus yn plus 1. And we will set that equal to b times xb minus xn. And so now, just as we did in the first section of this, we're going to get an equation here that isn't necessarily the final answer, but it is going to be one of our major important ones. So we'll have vn plus 1 over b times xn minus yn plus 1. And we'll set that equal to our xb minus xn. And we're going to square this off, even though it is not the final answer. It is a very important equation, and we are going to do there. And so now we're able to go into the second portion of this material balance. And so this algebra is actually going to take us 3 separate steps. And the first one will be writing out this vn plus 1 equation, again, times h times plus 1. We're going to add our b value times h bar at the boilant, and we're going to set that equal to our qb value. And added to this qb value, we're going to have v bar n plus 1, and then we're going to add b multiplied by h bar l n. All right, now from here we're going to have our second equation, in which we're going to kind of separate these into different polynomials. And so we're going to have v n plus 1 not by itself, but instead of 2 different terms here, we're going to create one giant polynomial, which would be h v n plus 1 minus h l n. That's going to be equal to qb value plus b times h l n minus h bar b. And now to arrive at the final equation, we are going to divide b into every single one of these terms, and you get v bar n plus 1 over b multiplied by h. You know what? We're just going to copy this. Duplicate it. Same thing there. And then this is going to be qb over b multiply minus h l n. This is actually a minus l n minus h b. And I'm sorry, I have this entirely wrong. You don't want QB, you want HL outside, you want to bring QB inside that parentheses, so you're going to have HLN minus, so that's why I had it, that is a plus, okay, minus HB minus QB over B. And now this is actually the final equation of our material balance for this. And now we're going to do the same thing and prove this with a graph. And so now before I even go into the next part, we're going to do the same thing where this is going to be our A, this is going to be our B, this is going to be our C, and this is going to be our D. And now we're going to do the same thing with our graph, but it's going to be a little bit different. It's not the exact same. So let's make this here. Again, this is going to be our H bar. This is going to be our composition. And then we're going to have our liquid line, our vapor line. This time, this delta D value is going to be down here. Or no, I'm sorry. This is actually going to be B. Wait. Sorry, this is still delta D. And instead of doing a straight vertical line, this time we're going to draw a line through both. That's definitely what I want. And this is going to have an intersection, and this is going to have an intersection. And then this time, we're going to be following these steps to as you go here and across and up. And this still has 4 different sections labeled A, B, C, D. So now we have proven that the second form of solving this is still correct because, like I said previously, instead of following a linear line to our target goal, we are taking a step-by-step function that is linear. I said that wrong. Instead of just taking a straight line, like imagine if someone told you to run from like home plate to first base. Imagine you can't just run a straight line. You can only take like little steps right and left on the way there. I don't know if that's the correct analogy I'm trying to make, but we have proven that we are going a different way, but we're getting to the same target using these equations, and that is what necessarily proves them to be a working function. And now we're going to move into Colab. So this is actually going to be quite a bit of coding, so I've already inputted our library, so that just lets us get straight into it. So the first thing we're going to do is say that P is equal to, oh, sorry, I just had a pop up. P is equal to props, and we want methanol and isopropanol. Alright, so now run that. Good. The next thing we're going to do is PHV is going to be equal to an array here of numbers 0.4 and 0.6. And then we also need this 350. All of these numbers are from the problem statement. Let's run that. Good. It gives us an array. Cool. Let's continue. Now, the next thing that we need to do is do the bubble temperature of our NRTL. We're going to have to define that, so we'll do bubble temperature of our NRTL, and we want that in terms of X and pressure, so our composition and our pressure. And in this, we need to do our T naught is equal to a sum of our X times P dot TB. Should be uppercase actually. And then we need to define the fruit here of our temperature. And we need that to return a value of the sum of this X times P dot NRTL underscore gamma. And this is going to be a function of composition and temperature again. And then we are going to take that and multiply this by P dot P vaporization of a function temperature. And then that will be minus 1. And here we want to get out of that defined fruit. And we're going to do T equal to SP. We need to optimize like we did in the last one. Optimize dot root underscore scalar fruit X naught equals T naught. We want our method to be the secant line. And dot root. Okay. And then finally we want this to return a value to us of our temperature our x times p dot nrtl underscore gamma. This long equation. So let's hope this works, and we are good to continue. So now, the next thing we need to do is actually say what our pressure is going to be, which is going to be 1 to the negative 10th power, which is going to be 1e, or negative 5th power, sorry, 1e to the 5th. And then z1s is going to be equal to a Lorentz space function of 0. Zero, comma 1, comma 1. And then we want our y to just kind of be an open bracket so things are able to go into it as we want. We need to say what the same thing for the bubble TS. This is just going to allow us to collect all the data values per step and store it in here as an array. And then for loop x1 in z1s, we need to do our temperature. We need to do our y1 underscore, and that is going to be equal to our bubble temperature of our nrtl. I'm going to make this an array of x1 and 1 minus x1. Also need our pressure in here. So let's scroll down. And then we need to, like I said, the reason we made these y1s and these bubble t just kind of an open bracket is so we could add into them. So this is what we're plugging in, bubble ts dot append, which means you're going to be adding stuff into there. And we want to add all of our temperatures. And then the same thing for here, y1 dot append, which means we're just going to be adding in. We're going to be adding all of our y1 values. So this is essentially so you're able to collect more than one value. You're collecting all the values along the way. So let's get out of this for loop. And we want bubble ts to be now an array of all of the bubble t best values, and the same thing. Great, let's run this. It says we do have an error here. Bubble TS not defined. Oh, that's why. Need an S right there. Okay, we are good to go. Now, we're going to do a lot of interpolate here. So honestly, I'm going to type it once and then kind of copy it so I don't have to keep typing it. So we're going to do x interp is going to be equal to sp.interpolate.p chip capital interpolator. And then so I'm going to copy this just so I can continue to do this. And then but then in here it's going to be different every time. This one we want y1s and z1s. And then now we're doing ty interp. Put that in there. And in this one we are going to have y1s, but then this time it'll be bubble ts. Same for here, we're going to do tx value interp. And in this one we want z1s and bubble ts. Now we want our HVS value, and that is going to be equal to bracket here, HV. And in this, we're going to have y1, 1 minus y1. And then still in these parentheses here, we have ty underscore interp, y1. Still in this here, we need to make 4 y1 s. and then HV interp, paste that in there again, and this one we have Z1S and HVS. Still have some more interpolating to do, so we now have HLS, and that is going to be equal to pretty much the same thing here with, oh, but with a few modifications. So this is actually going to be X, and then this will actually also be the same. Oh, come on. But this is going to be H liquid. So the first one was vapor. This one's going to be liquid. And this is going to be S there. Let's run this. Oh, I already see an error. I see an error right here. Yeah. Make sure this is good. Cool. So now we are able to plug in the actual values that we wanted for this. These are all specified in the problem statement. This is going to be 1, and just so we know, this is moles per second. And then our ZF value, as we were told before, is going to be 45. Our distillate, recovery distillate, is going to be 0.96. Our W distillate is going to be our RD value times our F value times our ZF value. Our X composition of distillate is going to be 0.98. Our distillate value is going to be WD divided by XD. Our boilant value, which we already said, F minus D. And then WB is going to be equal to ZF times F minus WD. And then XB is going to be WB. So now we have our R value, which is going to be equal to our liquid divided by our distillate. And for this, we're going to have 5. And I'm going to just write that as L divided by D. And then we need our QC value to be equal to our reflux times our distillate plus our distillate. And then this needs to be multiplied by HV underscore interp minus HL underscore interp. And just so you guys know, this is actually the condenser cooling down to its saturation liquid temperature. And then our delta D is going to be equal to that equation that we derived, QC divided by D plus HL interp XD. And the units for that are going to be joules per mole. And now there's a couple things that I'm going to put in here just so we know what we're doing. The number sign lets us do whatever we want without having any problems. So we're going to say H times HF plus QB is equal to QC plus B times HB. These are all from what we derived on the iPad, plus D times HD. And we're going to say HF is for simplicity. So HF is going to be equal to HL interp ZF, and then QB is equal to QC plus B times HL underscore interp D times. Sorry if I'm not talking very much. This is a lot of just typing and kind of plugging and chugging. Delta B is equal to HL underscore. Okay, let's run this. That was a lot. Let's run this and see if it works. We're good to continue. So now we're going to input our fruit for our rectifying and our fruit for our stripping section. So you're going to define fruit underscore rec. This is going to be functions of y and x, colon. And then we are also going to define fruit for our stripping section, which is going to be y and x. Now, this function is going to be hv equals hv interpolate y, and now our hl. And we need to return a value of delta d minus hv times y minus x. Okay. And now for this one, we're actually going to do like the same exact thing, but just making a couple changes. So we can copy and paste this, and this is correct and this is correct, but here we are going to swap this actually, and this is going to become hv minus delta b y minus x, and then instead of this xd minus y, we actually want x minus xb. So let's run this. We are good to continue. And so now we've actually come to the point of plotting all this, but this is going to be a bit much. This is going to take a while, so just bear with me. So fig equals make underscore subplots. We want rows to equal 1, columns to equal 2. Fig, now we're going to add a lot of scatters here. It's actually going to be 3, so we're going to do fig dot add underscore scatter, and we are going to copy this 3 times, get rid of this. And so inside this first one, do x equals z1s, y equals hv underscore interp z1s, and then we have row equal 1, call equal 1. It's actually going to be the same for this one. And then in this last one, we're going to have x equals xd, comma, xd, y equals hl interp xd, delta d, and then we want our mode to equal 2 lines. And we can make this any color we want. I like orange. It's my favorite color, so we're going to do orange. Enter here. I need to make a switch, which we're going to set equal to false. And then and then we want MC points to be equal to double bracket XD, close brackets. And then we want Y to be equal to XD. Now we need to make a for loop. So, as I said, we are now going to make a for loop for I in range 1000. Scroll down here. X is going to be equal to X interp Y MC points we're going to append this, and this is going to be equal to X dot item comma Y. And then make another if loop in here if X is less than X of our boilant value. We're going to break. And we need to do another fig. We're going to be using this fig.addScatter a lot, so we're just going to copy it again. Fig.addScatter, and here we want X equal to a bracketed Y comma X, and then Y to be equal to a bracketed HV interp and then we also need our HL okay, you know, actually I'm thinking about this. The we have completed all of the actual work to this problem, and at this point we are just plotting, which I've done a million times before. Everyone knows at this point you could watch it. So I'm just going to type this out as fast as I can off camera, and then I'll explain it once I'm back on. This doesn't necessarily apply to any of the math or problem solving. We're just plotting at this point. So I'm going to skip through this part and save you guys some watching time. So I typed it in all for the first time. And as you guys can see, we did not get at all what we were looking for. So I'm going to go back into this, figure out the problem, and come back to you guys once I figured it out. That took me absolutely forever. I could not understand what was wrong. It was all the way in the top. It doesn't matter. We're fine now. And what we're looking at here is the graph that I showed you, similar to the one on my iPad where we have up at the top right here. We have our delta t, bottom left we have our delta t, and you can see all these values stretching through, making vertical lines. And the thing that I want to look at here is our reflux ratio. Right now we have it set to 5. Let's see what happens when we set it to 1. Thinking. As you can see, it is completely shifted all to the right. It looks funky. You don't want a reflux ratio of run because that is saying to you that your liquid, the amount that is not what you want in the distillate, is getting closer and closer to the actual entire value of distillate. So that ratio is becoming worse and worse. And let's see what happens when you go to 10. As you can see, the lines become more spaced out. This is due to the fact that that liquid is becoming such a higher number compared to our distillate, which is the value that we are looking for. So this is the final part of this homework. Thank you for following along. I hope it was easy to understand and somewhat enjoyable. Thank you so much for watching. Have a good day.